Try to define what it means for a mathematical space to be two-dimensional without relying on your standard geometric intuition. If you have studied linear algebra, you have an easy answer. You simply count the basis vectors in your coordinate system. 2 vectors, 2 dimensions. But general topological spaces strip all of that structure away. There is no origin, there are no axes, and there is no concept of measurable distance. You cannot simply count parameters to find the dimension either. As this animation shows, it is possible to map a single one-dimensional line continuously until it entirely fills a flat two-dimensional square. Because a line can fold into a square without tearing, we need a coordinate-free metric to measure dimension, one that relies strictly on properties that survive these continuous deformations. In a general topological space, we rely entirely on one reliable building block, the open set. Instead of laying down a coordinate grid, we try to enclose the entire space using a collection of these open sets. We call this a covering. This text from Munkres provides the exact mathematical definition. An open covering of a space X is a collection of open subsets whose union equals X itself. Open sets, by their nature, do not include their boundaries. Because they lack flush edges, covering a space completely forces these sets to overlap. Determining topological dimension requires measuring the unavoidable thickness of these overlapping regions. We can analyze exactly how a specific collection of open sets behaves when it covers an abstract space. To measure the thickness of the cover, we introduce our first formal term, the order. Pick any single arbitrary point inside the covered space. Count exactly how many individual open sets contain this specific point. The order of the entire cover is the absolute maximum number of sets that intersect over any single point, anywhere in the space. Topologists use a specific indexing convention here. If a point sits inside a maximum of m+1 sets, the order is defined as m+1. This counting exercise successfully translates the abstract intersections of open sets into a strict, manageable integer. Checking a single arbitrary cover does not expose the limits of the space. We have to optimize the cover. This requires our second core concept, refinement. A refinement is a new collection of open sets where every new set is a subset of at least one set from the original cover. The inclusion relationship is strict. The finer mesh maps directly inside the coarse parent sets. Despite being smaller, this newly refined collection must still completely cover the underlying space without leaving any points exposed. We refine the cover to purposefully shrink the sets, allowing us to pack them efficiently and minimize the order as much as mathematically possible. Refinement strips away excess overlap, revealing the thinnest possible covering the space will permit. We now have the precise axioms required to build the Lebesgue covering dimension. A topological space X has a dimension less than or equal to m if every possible open cover has an open refinement of order less than or equal to m+1. The space's exact topological dimension is defined as the smallest possible integer m where this condition is true. The m+1 indexing convention ensures that a zero-dimensional space, like a set of discrete points, accurately resolves to an order of 1, meaning there is zero overlap. We have defined the dimension of a space using absolutely nothing but open sets and their intersection limits. We can test this abstract definition against a concrete intuitive space, the one-dimensional real line. Assume the line is initially enveloped by a chaotic, heavily overlapping open cover. Here is the base space and our unoptimized coarse cover. Now we construct a refinement using standard small open intervals, denoted as A to B. We organize and pack these small intervals tightly end to end to minimize overlaps. But because they are open sets, they lack hard, inclusive endpoints. They cannot sit perfectly flush against one another. To prevent a gap in the cover, the end of one interval is forced to slide slightly over the beginning of the next. At maximum density, these intervals only ever overlap in pairs. No single point sits in 3 intervals. This refinement achieves a maximum order of 2. Applying the Lebesgue definition, if m+1 equals 2, then m equals 1. The topological framework confirms that the dimension of a line is 1. This covering logic scales effortlessly, leading to the generalized theorem that the dimension of Euclidean n-space is exactly n. To cover a two-dimensional plane without leaving gaps, you need a grid of open sets. At the vertices of any 2D covering grid, a minimum of 3 distinct sets must overlap. An order of 3 means m plus 1 equals 3, resulting in a dimension of 2. As the geometric complexity of a space increases, the unavoidable structural intersection of its open covers scales to match it. Dimension in topology is not about coordinates, length, or vector bases. It is strictly a measure of intersection limits and covering density. The behavior of open covers serves as the formal basis for many topological properties, including compactness, as seen in Chapter 3. Stripping away geometric intuition to build pure, set-theoretic proofs is the ultimate goal of the Munkres text. If you found this helpful and want more clear explanations from standard books like Munkres, don't forget to like the video and subscribe to the channel.